Okay, so this is our last video from the notes, from the set of notes that I gave you all. So congratulations for those of you that made it through Hear My Voice for the third video almost. Okay, so just finishing up this problem and then one other problem and then we're done. Okay, so here we have a stone is shot. Yes, so we can start our problem now because I think in the last video I went over everything. Just again to reiterate, when you set the velocity function equal to 0, that represents the max height of an object. So think about if you took, let's say, a tennis ball and threw it up in the air. It's going to reach a maximum height. It's going to go up, all right? So it's going to go up at some velocity, and it's going to reach a maximum height, and then it'll come back down, okay? And so to find out what that maximum height is, you set your velocity equal to 0, and then you have to do a little more work. So we'll talk about that in part B of the problem, okay? So part A just says, well, let's read the problem. So a stone is shot with a slingshot vertically upward with an initial velocity of 50 meters per second. So this is our v sub naught, from an initial height of 10 meters. So that's our position function. So that's s sub naught. And it says find the velocity at t equals 2. Okay, so we have, oh, and I didn't mention, oh yeah, I mentioned it up here. That's the general formula for when we're talking about throwing an object, tossing an object up. That's the general function for position and velocity. You need to remember, if you remember position function, if you remember this function, then you can just take the derivative to find the velocity function. So ideally, you don't need to remember them both, but you do need to remember the position function s of t. Okay, all right, so we have this function. I kind of squoze it here, so hopefully you can read my writing. That's s sub naught plus v sub naught times t minus 1/2 gt squared, and that equals, with our given information, and again g is 9.8, so we can fill that in. So with our given information, that gives us 10 plus 50t minus 4.9 t squared. Okay, so now to find the velocity, we first need, to find the velocity at t equals 2, we first need our velocity function. So we take the derivative of s sub t, which equals 50 minus 9.8t. And so v sub 2, when you plug that in, you should get your answer. So that's what I want you to figure out. So just plug in 2 in there and get your answer. Okay? All right. Now let's look at part B. So part B says, what is the maximum height of the stone and when does it reach that height? And so round time, because it's when, that's your time, and height to the nearest tenth, okay? So again, remember, you have to set v of t equal to 0, and that'll give you at what time you're reaching, that stone is reaching its height. That'll give you t, okay? And solve for t. All right, and then we have to do more work to figure out what's the maximum height. So we're actually answering the second question first, when is it reaching that height, and then we're going to use that information to tell us what's the maximum height. Okay, so here we set our function was, I'm sorry, let's go back. So v of t equals 50 minus 9.8t. We got that from part A. And so we set 50, I'm sorry, my screen is moving, so let's do this. Okay, we set 50 minus 9.8t equal to 0, so that's a decimal point there, and we solve. So t equals, or I should say it's approximate because we're going to round it to the nearest tenth. And make sure you're really doing these calculations. Don't just write my answers down. Make sure you're checking to make sure you get these, because I could have made a mistake on purpose, of course. But no, make sure you check my answers, okay? So t is about 5.1 seconds. And that tells us, so that's when it's going to reach. So that's telling us, okay, when we throw it up in the air after 5.1 seconds, it's reaching that height, and then it's going to come back down. So that maximum height, we need our position function. So we need to go back to our original function, our s of t function. Okay, s of t when t is 5.1. And that's going to tell us what our height is. So not the velocity, because if we just plug 5.1 back into velocity, that's going to give us 0 because we set it equal to 0. So we have to go back to our position function. So s of t which equals, what was our position function? 10 plus 50t minus 4.9t squared. Okay, and so the answer is, I want you to tell me what the answer is. So how many meters, how high is that stone? Okay, the last thing we're going to do, and you guys will be done with the notes, is talk about acceleration. Okay, so find the acceleration of a ball tossed vertically in the air from ground level. So when it says from ground level, that means your initial position, your s sub 0 or s sub naught, is equal to 0 because it's from the ground, right? It's being tossed from the ground with an initial velocity of 12. So that's your v sub naught meters per second. So how does a sub t describe the change in the ball's velocity as it rises and falls? And no, acceleration is the change in rate of velocity. Okay, so it's change in rate. Whenever you hear that, you want to think derivatives. It's the change in rate of velocity. So if we think about it, so we start off with a position function. We know that if we take the derivative with respect to t of our position function, actually I don't want to write it that confusing. We know that s prime of t equals velocity, and so s double prime of t will equal the derivative of velocity, which equals acceleration. Okay, so again, recall our position function is s sub naught plus v sub naught times t minus 1/2 g times t squared. Okay, and we can just fill in our information. So s of t in this example, s sub naught is 0, so we just leave that. So 0, I'll write it just to be consistent, plus 12t minus 1/2 times 9.8, because that's our g, times t squared. Okay, and so that equals 12t minus 4.9 t squared. Okay, and so v of t, velocity, equals 12 minus 9.8 t, and thus acceleration, a of t, is equal to the derivative of v of t, and that just equals negative 9.8. Okay. So that tells us, and this is meters per second square, so that tells us that acceleration is constant. So as the ball rises and falls, its velocity decreases from 12 to negative 12 at the constant rate of g. Okay, and we're going to talk more about this. So if you're not clear on what's going on, but basically graphically, when we get into more graphically looking at derivatives and slopes, remember, derivatives represent slope. So the derivative of a line would just be a constant, since the slope on the line is the same everywhere, right? So when we have like a parabola or some curve, at different points on that curve or that line, the slopes will be different. The tangent lines are different. But if you have a line, which is what we have in our velocity function here, then its derivative is just going to be a constant. Okay, we'll talk more about that. So we're done. I didn't want it to take this long, but at least it's less than 50 minutes class time, so you guys are getting a bargain. Make sure you go over this and make sure you understand what's going on. I'll answer questions on Friday because, again, Thursday we have a guest teacher. Okay.